You are standing up AI inference across a dozen geographically dispersed sites. The data scientists have handed you a trained model. The question is where it runs. Does every site phone home to a central endpoint for inference, or does a model copy live at each site and execute locally? That choice drives one dependency, per, site swap C, latency budget, data sovereignty requirements, and how you behave during a link failure at peak operational tempo. Centralized model serving means one inference endpoint, a GPU cluster in a data center or private cloud, and every edge site forwards input data to that endpoint, receives predictions, and acts on them. The model lives in one place. You update it once. You monitor one accelerator fleet. If a bad checkpoint ships, you roll it back once and all sites realign immediately. The economic argument is strongest at low site counts. Instead of provisioning a GPU node at each of 12 sites, you run a shared cluster and let utilization averaging work in your favor. A T4 per site idling at 15% utilization costs more than an A100 cluster running mixed workloads at 70%. The failure surface is the network path. Every inference call is a round trip to the center. Congested, lossy, or severed, WAN means the edge site is either blind or falling back to degraded heuristics. In contested environments or sites with sub-10 Mbps uplinks, that round trip is not acceptable. And if raw sensor data, full motion video, RF captures, acoustic signatures must be forwarded before inference, you are burning WAN bandwidth on every query at every site simultaneously. Federated model serving pushes model weights to each site during a deployment window. Inference runs entirely locally. If the WAN link drops, inference continues. The latency profile changes fundamentally. You are not measuring round-trip time to a data center. You are measuring local forward pass latency on the hardware at the site. On a Jetson AGX Orin or an AMD Instinct MI100, most vision and signal classification models complete in tens to low hundreds of milliseconds. For fire control loops, autonomous navigation, or real-time spectrum deconfliction, that margin is not cosmetic. The cost structure inverts with site count. At 2 sites, paying for GPU compute twice is expensive. At 25, the operational overhead of centralized serving WAN bandwidth contracts, redundancy engineering, latency SLA management, frequently exceeds the capital cost of deploying COTS edge accelerators. The inflection point sits between 8 and 15 sites depending on model size and per site inference rate. The operational burden is real. You maintain N software stacks, N hardware nodes, and N model version states. Version drift, where sites diverge due to partial deployment failures, is a live risk that requires dedicated detection and remediation tooling most programs underestimate at the outset. 5 dimensions separate these architectures in practice. WAN reliability is the first. What is your P99 link availability at each site under peak operational load? Inference latency budget is the second. Applications tolerating 200 millisecond round trips behave differently than those requiring sub-50 millisecond local response. Model VRAM footprint is the third. A 7 billion parameter model needs roughly 14 gigabytes at FP16, and not every edge node carries that headroom. Site count is the fourth. As N grows past 10, the economics of local compute begin to favor federation. Data sovereignty is the fifth, and often the hardest to negotiate away. Classification boundaries, ITAR restrictions, or data residency requirements may prohibit forwarding raw sensor data off-site entirely, regardless of what the latency math says. On WAN-connected, latency-tolerant workloads with fewer than 10 sites, centralized serving wins on total cost of ownership. Unified model governance, centralized logging, single fleet accelerator management, fast update cycles, push once, all sites align within minutes. The shared cluster handles burst load better too. If one site needs 10 times its average inference rate, the central pool absorbs it. Federated serving is bounded by local hardware with no burst headroom. On DDIL environments, degraded, denied, intermittent, or limited connectivity, federated serving is a requirement, not a preference. A model that cannot reach its endpoint during the operational period it was designed to support is a liability, not a capability. Federated also wins whenever raw data cannot leave the site. Classification boundaries or legal data residency constraints make the architectural decision before any latency analysis starts. Model update logistics reverse the advantage. Pushing a new checkpoint to a centralized endpoint takes minutes. Pushing to 25 federated nodes requires staged rollouts, per-site deployment verification, rollback logic for partial failures, and a source of truth registry tracking what version is actually running where. That pipeline is buildable. It is not free. Centralized serving degrades non-linearly under high operational tempo. When every site simultaneously drives peak inference rate, WAN contention compounds with inference queue depth at the cluster. The failure is not binary. It is a latency creep that looks like normal variance until queries are already stale and decisions have been made on outdated outputs. The second failure mode is data volume. If each site generates 100 megabits per second of raw sensor data and the model requires the full signal, you are not running a model serving problem. You are running a WAN capacity problem wearing an AI label. Federated serving breaks when the site hardware cannot support the model. A 70 billion parameter model at FP16 requires roughly 140 gigabytes of GPU memory. That is 8 A100s in a data center, not a node you are shipping to a remote installation. If your model roadmap trends larger, federated serving forces quantization, pruning, or distillation trade-offs that need explicit validation against operational performance thresholds, not assumption of neutrality. Centralized wins when you have reliable WAN latency tolerance above 200 milliseconds, fewer than 10 sites, and no data sovereignty constraints. The economics favor it, governance is simpler, and you avoid operating N-independent inference stacks. Federated wins when connectivity is unreliable or contested, when latency must stay under 50 milliseconds, when data cannot leave the site, or when site count exceeds 15. The switching cost matters here. Moving from centralized to federated mid-program means qualifying edge hardware, rebuilding deployment pipelines, and rewriting the monitoring architecture. If there is any realistic probability that your operational environment includes DDIL conditions, at program start or at any phase thereafter, design federated from day one. Centralized aggregation and telemetry can be layered on top of a federated foundation when connectivity is available. Local inference capability cannot be retrofitted into an architecture that was built to depend on the network. The architecture that performs well in a stable environment is not the one that matters most. In multi-site edge deployments, the environment stops cooperating eventually. Contested links, node failures, operational surges. Design for that floor first. Everything above it is optimization.